So I'm Francois Petrelis. I work at École Normale Supérieure in Paris. First, I want to thank the organizer of the program for having me here. So today I'm going to talk about the dynamic of the magnetic field generated by dynamo instability. And first, I will present some system in which this dynamic is of interest. So first, the Earth. So we know that at the surface of the Earth, there is some magnetic field. This magnetic field is actually generated deep inside the Earth, in the liquid core. And if you measure the magnetic field at its surface, then you can see that it's roughly a dipole. And if you average over a few thousand years, this dipole has an axis roughly parallel to the axis of rotation of the Earth. So already the problem of how this magnetic field is generated is very interesting. But I'm not going to really discuss that. I'm going to be more interested in other property of this field that has been identified by Bruns in 1906, so more than 100 years ago. We realized that if you go back in time, the direction of this field has not been constant, but that it reversed. So you can therefore plot what is called a chronograph that gives you the direction of the dipolar field. In black, it's the actual direction, so it's pointing toward the source. And you see in the last 5 million years that this direction has changed from source, north, source, etc. It seems to occur frequently with an average frequency of 200,000 years, but with a large variation in the duration between reversals. So there is some randomness in this process. Another object that has some dynamical evolution of the magnetic field is the sun. So the sun also generates some magnetic field by dynamo instability. And in the last 30 years, it has been possible to measure the magnetic field at the sun's surface. From this measurement, you can you can do some spherical harmonic analysis of this magnetic field. And here I have extracted from this paper, from the Knackenston flow, the behavior of the dipole component of the magnetic field. And you see that it oscillates here with the 22 years period that we all have been aware due to the study of sunspot. So if you look only this dipolar component, it oscillates in a roughly periodic fashion. So I'm going to give just a few words on the origin of this magnetic field. And it's Larmor in 1919 that gave the explanation for the origin of the magnetic field. He says that the idea is that inside this astrophysical object, you have some liquids that can conduct electricity. There is some flow of this liquid, and then by instability, the system can convert mechanical energy into magnetic energy. If you want to describe this process, you need an equation that describes how the magnetic field evolves. So it's a bit shortened. So the evolution of the magnetic field is the competition between two terms. Oh. What should I do? Oh. Okay. So I continue. Okay. So it's a competition between two terms. Yeah. Oh. It's okay. It's fine. So one term is the induction. Comes from induction here, and that's the Joule effect. So maybe at that point I should introduce a dimensionless number that compare. So the magnetic Reynolds number that compare induction over dissipation, and that has this form. So that's a dimensionless number pertinent for this equation. Now, if you want to describe the evolution of the velocity field, you take the Navier-Stokes equation, plus you have a new term that comes from the Laplace-Lorentz force, so how the magnetic field modifies the velocity field. So I'm not going to say a lot about it. Just what I want to, maybe we should identify one thing is that there is some general invariant in the problem. If some magnetic field is a solution, B0, then you can see that the opposite is a solution. So you have always this invariance big is minus b in the problem, because this one is linear and this one is quadratic in B. Another thing of interest is that for all the systems we're going to be considering, the flow will be very, very turbulent. So if you want to give some dimensionless number for the second equation, then you introduce the kinetic Reynolds number, VL over nu. And there is something important is for fluids that conduct electricity is that this one, the magnetic Reynolds number, I will rewrite it VL over some diffusivity, where the diffusivity is obviously 1 over mu 0 sigma. And then if you write the ratio between the magnetic Reynolds number and the kinetic Reynolds number, it's another dimensionless number that is called the magnetic Prandtl number. And it's the ratio between the two viscosity. You can see? Okay. So this number is very, very small. Where does it come from? It's because it relates how impulsion is transferred in the system compared to how electrons, how current is transferred in the system. And you see that the two processes are not controlled by the same physical object. One is controlled by the electrons and the other one by the atoms. So that's why this number is so small. And what it means is that you have this inequality. The magnetic Reynolds number will be very small compared to the kinetic Reynolds number. So even at onset of instability, suppose the onset of instability is magnetic Reynolds number of hundreds or 10, whatever. The kinetic Reynolds number will be very large. So the system will be fully turbulent. The other way to see that is, suppose you're in a system where you have dynamo action. It's not because the kinetic Reynolds number is very large. The kinetic Reynolds number can be very large, so the number of degree of freedom of the velocity field can be very large. But for what concerns the magnetic field, you might be close to the onset, and only a few modes could be involved in the dynamics. Okay? So no. Yeah, sure.
Are you thinking mostly about the geodynamo? So in the geodynamo, the nonlinearities are coming primarily not from U dot grad U, V dot grad B, but from the interplay between the thermal field and the magnetic field. So is Reynolds number relevant at all?
So, yeah, I present it in a simple way. And just here the equation I didn't consider neither rotation, neither which term will be forcing the flow. And of course, depending on the parameter, we could be in a regime where the effective Reynolds number could be small, would be not very large. I'm not even sure that for the Earth it's known if the flow inside is very turbulent or not so much turbulent. So how much the rotation influences the turbulent property of the flow. But I think that for this kind of flow, astrophysical, it's clear that there will be the number of degree of freedom involved in the kinetic energy, in the velocity field will be far larger than the number of degree of freedom involved in the magnetic field. That I think will remain, even if the turbulent property are a bit modified by rotation.
Are we to think of the Navier-Stokes equation as having added to it a buoyancy term to represent convection?
Oh, yeah. So, as I said, I just wrote this equation to discuss a bit the property of the system. Of course, if you want to describe the flow inside the Earth, of the system inside the Earth, you must add a forcing term here that describes how thermal convection or compositional convection will drive the flow, and then rotation. Anyway, I'm not going to discuss this equation after. I just wanted to identify two important points. First, that the flow will be very turbulent, and second one, the invariance in big is minus b. Okay? So I'll proceed, maybe. So I come then from a few results that have been obtained from the von Karman sodium experiment. So it's a collaboration that involves three groups. One group in Saclay, led by François Daviau, one group in Lyon, led by Jean-François Pinton, and a group in Paris that is led by Stéphane Fauve. I have just written in red the PhD student working on this experiment. And this experiment study liquid sodium flow that is generated inside a cylinder. So you have here a picture of the cylinder. So this cylinder is full with liquid sodium, around 150 liters of liquid sodium. Temperature is maintained above the fusion temperature of sodium. And the flow is driven by two propellers here, two disks that in general will counter-rotate. And motors input mechanical energy to these disks. The power is around 300 kilowatt total, which allows to reach very, very large kinetic Reynolds number, more than around 1 million. So there is another line here that disappeared, in which, and I'm not hiding it, it's written that we had the last change, we use soft iron disks, okay? So our understanding of the effect of soft iron disk is that it modifies the boundary condition and it promotes the instability. So it's written here. So now I go to a few results we had. And I will first discuss what happened when the two disks exactly counter-rotate. Okay, so I have two disks facing each other that exactly counter-rotate with the same speed. So what is important is to realize that there is some symmetry in that case. Actually, any axis that goes through the midplane of the cylinder is an axis of invariance if you rotate by pi. Okay, so if you rotate by pi, this experiment where the two disks rotate with the same speed, then you find the same forcing term. Okay, so we have this symmetry in that case when the two disks exactly counter-rotate. So if we increase the velocity of the two disks from a low value, 10 Hertz, where we have no magnetic field, then above some critical value, we see that the magnetic field increase and saturate around and reach a finite value around which it will fluctuate. So the exact value here, the different components are related to the spatial structure of the mode. Now we have measurement at different positions in the experiment, and we can say that the mode when the two disks exactly counter-rotate has this structure here, time average mode. So it's an axial field going from an axial field like that in green, and so that's the poloidal field, and some toroidal field in red. And of course, we can have this solution or the opposite, so plus or minus. We see that this solution breaks the symmetry actually. It will be odd. I mean, this mode is odd under the rotation symmetry. And for people maybe who are used to the geodynamo context, they could be surprised that the toroidal field here has the same direction in both hemispheres of this cylinder. It's because the symmetry are different. Okay? Here the symmetry is the symmetry on the rotation of pi in the midplane, whereas for the Earth, you're expecting a symmetry under equatorial symmetry. I will go back to that later. And another point that is important, that it's written here, is that when the two disks exactly counter-rotate, there is no reversals. Okay? It's a bit surprising because if you get very close to the onset, the magnetic energy can be very small. It vanishes at onset, I think. So it can be made very small, so very small compared to the kinetic energy of the fluctuation, and in exact counter-rotation, that's the regime where you have more fluctuation. And then even with this difference between the magnetic energy and the kinetic energy, we have not observed reversals. Okay? Now, what we can do is rotate one of the disks faster than the other one. And then we will see. So it amounts to add some global rotation to the flow in some sense. But I think more important is that it will break this symmetry under rotation. If this disk rotates faster than this one, then we don't have any more this invariance by rotation around here. All right?
Can I just ask you a quick
Sure.
question? You know that red line you put up there, indicating a sort of saturated state?
Here.
What's the ratio of the magnetic energy to the turbulent energy?
Okay.
That regime?
So it's a very good question. It seems to be dimensionally you can write, we verify that Becker.
I don't want to slow you down. There's a quick answer.
Yeah, anyway, there is some prefactor and then it's a function of the magnetic Reynolds number. Okay, so if you want, I even forget about the prefactor here. And what is important is that this function at onset will goes to 0. So the magnetic energy can be made as small as you want compared to the kinetic energy that has a finite value at onset.
I understand that, but how big can it be made?
How big is the coefficient here?
No, how big can F be made? Or is it monotopic?
Oh, how large can it be compared to? That will depend on the range of parameter we can reach, but in general, the maximum magnetic field we have had is a few hundred Gauss, maybe 500 Gauss maximum. So you want to see how it compares to kinetic energy?
I'll ask you, yeah.
For equipation, it's okay.
You carry on with your talk, I'll ask you.
Yeah. It remains very small compared to the kinetic energy of the flow. Yeah. Yeah, I was more interested. Okay, sorry. So I was more. I wanted more to insist on the fact that even when this magnetic energy is very small, and turbulent fluctuation very large, they don't drive reversals between these two states that are supposed to be not very different. Okay. So what happens if one of the disks rotates faster than the other one? Then I can draw a parameter space in which I plot the frequency of the slow disk as a function of the frequency of the fast disk. Here, and I have two parameters now. So the diagonal here is the case where the two disks exactly counter-rotate, so that's the state I described just before. And hollow symbol stands for no dynamo. And then if we go along this diagonal here, above some value here, you have these empty symbols in blue that stand for stationary dynamo. So here we have a dynamo as we described before. And in blue, that's what I call a stationary dynamo. I mean by that there are no reversals. And you see that there are these red domains here that are associated to dynamical regime. So I'm gonna go in detail into some of this dynamical regime, but then the direction of the magnetic field will reverse. Okay, you see that these domains are far from the diagonal. So when there are this symmetry, the rotation of pi. Okay. So let's go to these dynamical regimes that we observe here. So here is a time series of the measured magnetic field at some position in the experiment. It's in the mid-plane, if you want. So I measured here. It's measured here. So you see that the component oscillate in a really nonlinear, with a really nonlinear oscillation. The green component has some plateau and then suddenly switch to the opposite value, while the red increase, some slowdown when the other one has a plateau and then reverse. So it's interesting to compare this dynamical regime with the stationary dynamical regime in its vicinity. So to do that, I'm going to plot a phase space of this oscillation, which means I plot one of the component as a function of the other component.
Sure. Can you measure velocities as well as fields?
Say again?
Can you measure velocities as well as fields?
We're working on it, but for now we don't have measurement of velocity. It's difficult in liquid metals, so we don't have right now.
So you don't know if the flow is following some similar switching from one regime to another?
We don't know, but I mean, we have some measurement of the input power, and we see in this regime, for instance, we don't see any change in the input power in the system. Okay, and you will see that our understanding of this dynamical behavior do not require any change, any change in the large-scale flow and in the characteristic of the flow. Okay, the idea is that these magnetic fields are not very large. If you're close to onset, the Lorentz force, which is quadratic in B, actually at onset goes to 0, so do not modify really the behavior of the magnetic field. I'll go to the description of that later.
The X, Y, Z components of the magnetic field at a specific point.
Exactly. So I don't want to go in detail on which one is which one, because I'm going to give you later, explain you later which one is associated to which mode. So.
Which component are these? Which is the toroidal component?
Okay, so the toroidal component is the red, and The green here at this point is a poloidal component. In the next slide, or 2 slides later, I will explain why it's like that. So now I go to the phase space representation of the system, and here, so you have this oscillation that I just showed you. So these phases are the slow phase, and the system described like a cycle, highly nonlinear. So it's interesting to compare this trajectory in phase space to the state of the system when you go from, in black here, I have the case exact counter rotation. So that's the dipole state. It fluctuates around some value. Then I increase the difference of velocity between the 2 disks, and the stationary state is modified to this state here. If I increase further the difference of velocity between the 2 disks, then I go to this length cycle in red. If I increase further, then I find again a stationary state that is in green here, and increase further, pink one and blue one again. So what is interesting is to superimpose these 2 curves, and you see that they fall on the same, that the stationary state fell nicely on the limit cycle. So how do we understand that? It's that in this state here, we are in a dipole state, dipolar state. And when you increase the difference in velocity, then the system evolves with some quadrupolar component. And then here, this state here is a quadrupole only, with this. Like that's a sketch of the quadrupole. So if you look, like the quadrupole has a large R value in the midplane, but a very small x and theta value, actually 0 value in x and theta. So this state here is a quadrupole, whereas this state here are associated to dipole. And you see that all this process here of nonlinear oscillation is actually the evolution of the system from a dipole to a quadrupole, and in a cyclic way. So let's go to another regime we obtain when we change the parameter. And that's a time series. Observe the magnetic field, same kind of measurement, same position. So the magnetic field fluctuates around some value for very long duration, hundreds of seconds. So the time scale, that's 30 minutes. Okay. So for hundreds of seconds, minutes, it remains the same polarity, and then suddenly reverses and reaches the opposite polarity. What can we say is that the duration of a reversal is very short compared to the waiting time between reversals. You can identify also a few properties. Here you can see that there are events where the magnetic field goes very small, here, maybe here again. So that, in the language of geophysics, is what is called an excursion or an aborted reversals. System start as if you wanted to reverse but go back, does not reverse. What can you see also is that at the end of a reversal, magnetic field reach large value before going to the saturated regime here. So this value here will, in most cases, larger than after. That, in the language of geophysics, what is called an overshoot. There is an overshoot at the end of reversals. It's interesting to see how this behavior is modified if we change some parameter in the system. So if we, very close to that state, if we change the velocity of one disk, we find again a stationary state, which is one of the polarity here. Stationary, then I change the velocity, I go to this random reversal. And then if we increase the temperature, we modify the parameter of the system, kinetic Reynolds number and magnetic Reynolds number. And we see that when we increase the temperature, the system evolves from random reversal to roughly periodic oscillation. So the frequency increases, and it evolves from this kind of, where the waiting time are far distributed, to a regime where the waiting time are less distributed. And that's happened with a very small modification of the kinetic and magnetic Reynolds number. So now I'm going to come to try to present you some modelization of this kind of transition. So it's work that has been done with Stéphane Fauve, Emmanuel Dormy, who is at École Normale Supérieure and Institut de Physique du Globe, and Jean-Pierre Vallée, also at Institut de Physique du Globe. So it's based on we make the hypothesis that the dynamical behavior of the magnetic field is of low dimension. And that's something that seems very reasonable because for the experiment, for instance, we know that we're close from onset because onset is it's 30 and we reach like 50 in magnetic field as number. So we know that we're close from onset. And for the Earth, well, it's so debated, but some people believe that it's not very far above criticality, so close to onset. So in that case, you might expect that only a few modes are involved in the dynamics. And we're going to also use symmetry properties of the mode we're considering. So there have been work before, some people here also related to modelization of the dynamic, and so I cannot cite my preprints, but they're here. So let's just describe which mode we're going to consider, and what is important is how they are related to the symmetry of the system. So for the VKS experiment, we have already seen that there is an invariance by rotation. When there is an invariance by rotation of pi, we have a dipole, and cis mode is odd under cis rotation. We have also seen that a quadrupole field can be involved. I have sketched it here, and it's a mode that, well, cis1 is odd, cis1 is even under the rotation. So they transform differently under the rotation. For the Earth, the Earth does not display cis symmetry of rotation, but it's convection between two spherical shells in a regime where it's rapidly rotating. So you expect an equatorial symmetry of the system instead of a rotation invariance. So with cis symmetry, you can define modes that are odd and even under cis transformation, and you realize that a dipole field that I have sketched here is a mode that is even under the symmetry, whereas and you can also construct another mode, a quadrupolar field that will be odd under cis symmetry. So at this stage, you should think that I'm confusing odd and even, but there are polar vectors, so they don't transform the same way under planar symmetry. But I might confuse sometimes. Anyway, what is important is that they transform differently under cis transformation. One is odd, one is even, and we will use that later.
Can I just ask, so S indicates reflection in the equatorial plane, does it?
Say again?
S indicates reflection in the equatorial
Yeah,
plane.
yeah. So when I look how cis mode are under cis transformation, how do they behave? Is they odd or even?
And dipole, you say, is even.
Dipole is even because it's a polar vector. So current transform normally in magnetic field. Anyway, what is important?
The blue circles, he has a movement field, is that?
Say again?
The blue circular
Yeah.
representing the S.
Okay, that would be the toroidal, that would be the poloidal, and that would be the toroidal field. And in for axisymmetric magnetic field, it's toroidal, it's azimuthal. And at that point, I want to mention, I'm not sketching what I think is the magnetic field inside the Earth. I'm just giving an example of what is a dipolar field and what is a quadrupolar field, with the definition of being that they transform odd and even under the cis symmetry. But the realistic mode will be more complicated. They might have more harmonics, but one will be odd and one will be even. Okay, I'm not saying the modes are like that; they're more structured. But we're gonna develop the dynamic on two modes: one that is odd and one that is dipolar, and one that is quadrupolar. So to do that, I write the equation, the amplitude of the magnetic field as some amplitude times the dipolar structure plus some amplitude times the quadrupolar structure. And close to onset, you expect that you can find an equation that relates how these two amplitudes evolve. It's a normal form approach to the problem. So I define, for simplicity, I define A, which is the dipole amplitude plus I, complex imaginary number, times Q. And we expect that close to onset of instability of cis mode, I can write the derivative of A will be a function of A and the conjugate of A bar. And I expect I can expand this function in powers of A and the conjugate of A. So that's what I do up to the first non-zero nonlinear term. And there is no quadratic term due to the invariance b gives minus b of the problem. So we must go to third order to have non-linearities. And now what I'm going to do is I'm going to look for a phase equation, which means I write the amplitude as A as some amplitude times exponential I theta, and this phase here will be related to the importance of the dipole and the importance of the quadrupole. Okay, on theta I can find D and Q. So I can write the general expression for the phase from that. I'm gonna, just for the discussion, use the simplified expression here, in which I have set some term to 0. And the important one being one of the, I have taken the simplest nonlinear term, but I could work on the general expression without loss of generality. I just do that for presenting it in a simpler way. So in that case, I get this expression for theta. The derivative of theta is mu I, one of the imaginary part of this coefficient, minus nu r, the real part of this coefficient, sinus of 2 theta. It's until now I haven't said anything complicated. No, what is important to realize is that when you have a symmetry, the invariance due to this symmetry will give constraint to this coefficient. So when the forcing is symmetric, you expect to have invariance when D is changed in minus D and when Q is changed to Q. Not changing. So, which means when the amplitude is changed in minus, it's conjugate. If you do that, and you plug it here, you find that all the imaginary terms, when in the symmetric situation, should be 0. And in this equation here, it means that the mu I should be 0. So, as a consequence, if you evolve away from the symmetrical configuration, then you expect that this coefficient increase. And we'll see that this will have a drastic consequence on the behavior of the solution. Okay. So, to discuss a simpler case first, let's see what happens if instead of sine 2 theta, I have sine theta only. So it's a system we all know. It's a viscous pendulum subject to a torque. Then the equation is, it's viscous, so I forget about inertia. Theta dot is minus sine theta plus the torque. Okay? And then if the torque is 0, I know that my pendulum has only one solution going down. One stable solution, sorry. But it has also one unstable solution that is sketched in red here. And when I increase the torque, what happens is that the stable solution goes in that direction, and the unstable solution goes in that direction. That continues, that gets closer, until C is equal to 1. When C is equal to 1, they collide. And if C is larger to 1, they have disappeared. So that's a bifurcation which is called a saddle knot bifurcation that describes how a stationary solution evolved into a cycle of finite amplitude. Saddle knot bifurcation. Time series of the projection of the position of the pendulum as a function of time gives this kind of behavior. So they remain for a very long duration close to size point, and then go very fast the opposite direction and come back and evolve very slowly here. So from that we can go directly to what happened from my magnetic field. It's the same equation, but I had a 2 theta here, which means that instead of having 2 solutions, I will have 4 solutions, and increasing the coupling, we get this solution closer. So let's see what happened. So that was my equation, mu I minus mu sine 2 theta. So when mu is 0, I have 4 solutions, one at 0, one at pi, that's the dipolar solution, one at pi over 2, one at 3 pi over 2, that's the quadrupolar solution. If I increase mu I, this solution gets closer. So here I have sketched the phase space of the system. Blue is the stable solution, red is the unstable solution. And if I start for the system is eventually attracted to a cis solution or cis solution. And if I increase mu I, then when mu I gets larger than mu R, you don't have any solution, stationary solution, and the system evolves toward a limit cycle. Another description maybe that is of interest of this transition is to write this equation as the evolution of a particle in a potential well. If I write the potential, I can calculate it explicitly. It has this form. And we see that if mu I is small, then the potential will have local extrema. Local minima are associated to the stable solution in blue, local maxima to the unstable solution. And if we increase mu I, then we will evolve from a system in which we have these different extrema of the potential into a system in which the potential is monotonous. And for the particle, it means that we go from a regime where it's trapped in one of the solutions to a regime where it evolved periodically. Okay? So let's compare this bifurcation with what is observed in the VKS experiment. What I can do is to prescribe the dependence of the different coefficients of my normal form, say how they depend on the difference of velocity between the two disks. Okay? So doing that, that's something I can choose, and I can have a system. If I increase f, then I evolve first to stationary solution, and then if f is large enough, to some highly nonlinear oscillation. These highly nonlinear oscillations resemble what is observed in the VKS experiment. You see that the green is displayed plateau, same as some plateau observed here, whereas the red increase and slow down when the green has a plateau. And now we can make it a bit more quantitative by saying I can set how much this amplitude in the normal form corresponds when I measure the magnetic field in the experiment. So I can set the conversion factor between the amplitude of the dipolar component and what is measured, and the amplitude of the quadrupolar component and what is measured. During that, I can do that and try to superimpose these with a time series here. So I take two periods that are quite periodic, and then I can superimpose. So the numerically computed solution of the normal form and what is observed. So in blue and black, that's the solution numerically, and in green and red, that's what is measured in the experiment. So it seems to be a nice agreement. There are some. Are
you going to tell us how you got your toy model equations? Are they derived from the original fluid dynamic?
No, I'm not going to do that.
Can you just give us some hint, or is it just an arbitrary toy model you wrote down?
It's not an arbitrary toy model. It's a normal form. So it means whatever the equation at the beginning, the symmetry constrains the form of the normal form. So the coefficient will the coefficient.
It's the simplest dynamical system with those symmetry properties.
Exactly.
Okay.
And the value of the coefficient will depend on some particular property of the flow, if there is more, I don't know, poloidal, toroidal. But whatever the system you will consider, if you go to third order in the amplitude of the magnetic field, you will have this kind of equation.
And how many disposable coefficients did you have to fit that?
That's my point. So there are many coefficients here. So it's clear that fixing the coefficient, you could fit a bit any kind of.
I think any ratio you want. If you measure the field at some other point, the ratio between the azimuthal and the toroidal field will be arbitrary. But at a different point, it goes from 10 to 0.1 to 100 to.
No, I don't get. So again.
The ratio of the azimuthal to the toroidal field that you measure will depend on the point you're measuring.
Sure.
So it could have any value.
Sure, and that will be related to what is the spatial form of the mode I'm considering. Okay? So, if I go to some other position, I can change the amplitude of the mode, like my dipole and my quadrupolar. When I go back to the initial magnetic field, here, what I measure here, I have, this amplitude, that are solution of the numerical equation, and this spatial structure here that will depend on the position in space. Okay, so they can have different kind of the time series will always be obtained from that and can look different. Because like if the dipole is very large compared to the quadrupole, I will only see that. If the dipole is very small compared to the quadrupole, I will only see that. If they're comparable, I will see one more than the other.
Francois,
Yeah.
you showed the comparison with the experiment, and looking at that simple-mindedly, you seem to have 6 complex numbers that are the coefficients: the nu, and the 4 betas.
Yeah.
Are they all to fit your data, or do you have external ways to calculate those?
No, we don't have external way to calculate them.
You could.
Be-
We've got 12 numbers.
it means you could, yeah, if we're able to parameterize which
It's a lot of
effect.
work.
Huh?
It's a lot of work.
Yeah, and it means you really understand what are the processes that make the dynamo grow. Okay, the system is very turbulent, so you cannot make a direct truncation of and obtain the coefficient in the normal form. Okay, it's not like really linear convection.
So the next point is that figure you did is the best fit with 12 adjustable.
Oh, yeah, there are many free parameters. Exactly. So what I can do is I can set the parameter even to follow the stationary point and then get the limit cycles. I'm not saying I have the minimal model. I just say that I have a model and I will recover all the behavior. Then exactly, I'm not arguing if I have the minimum number of coefficients. I will already show that we have the different behavior and the good organization of the system. Yeah.
The equation for A
Yeah.
looks like something Landau's order parameter expansion. And then usually this kind of approximation works only for some vicinity or particular range of A. Is it correct?
Yeah, but that's a normal form approach to the interaction between two modes close to their onset. So
it's correct only in some small domain.
sure. It's when actually you have to have two modes close to their onset and see the coupling term will tell you how they evolve one with respect to the other one. Okay, that's that is done in normal form approach to bifurcation system. Okay, so I'm not arguing on the number of parameters. So, where was I? Any other question? Maybe I proceed. So, until now I have only discussed this nonlinear oscillation. No, I haven't taken into account turbulent fluctuations. Okay. No, consider a system just below the onset of the saddle node bifurcation. So it's just before we get this periodic orbit that connects the 2 points. And consider turbulent fluctuation. So these are the two states initial here. And suppose you have turbulent fluctuation. So it will make the particle here fluctuates around this position. And then if fluctuations are large enough or act coherently enough for a long time enough, then it might push this particle above the top here. Then if we cross this region, the particle is not more attracted to this state, but will be attracted to the opposite state. And that's a reversal. What else can you say? Reversals are made of two phases, and the initial phase in which fluctuation act against the deterministic dynamics, and the second phase in which the deterministic dynamics help the evolution. So we expect that the first phase will be slow, whereas the second phase will be faster. What else can we? You can also realize that some fluctuation will push the system close to the boundary here, but will not be. It will not be sufficient to push them far enough so as to be attractive to this point, and the system then will go back to the stationary solution here. So that's an aborted reversal or an excursion. You can compare the end of a reversal with the end of an excursion if you realize that the end of the trajectory depends on the direction of these 2 points, and you see that reversals end up and reach the stationary solution from larger value, so we'll have an overshoot, whereas excursion will not have an overshoot. So some prediction from that. So we have a mechanism, and we predict the mechanism and the shape of reversal. So it comes from a coupling between dipole and quadrupole when a flow symmetry is broken. The system will be, the reversal will be made of two phases, a slow phase followed by a fast phase. And we can also predict the origin and the shape of the excursion. So excursion are aborted reversal, and the initial phase is similar to that of the reversals and ends up without an overshoot. You can say a bit more by the analogy with the particle in a potential well. Actually, you can predict the statistic of the reversals. Because this problem actually, in the context of random dynamical system, is equivalent to excitability close to a saddle node bifurcation. And in that case, it means that what controls the waiting time between reversal would be the time that it takes for the particle to get out of a metastable potential well. So you know that this is distributed exponentially with some characteristic time here, and that for the normal form you can calculate this characteristic time. It depends exponentially on the difference of energy between the minimum and the maximum of the potential, and D is the noise amplitude. What is interesting in that law is that this time here, the average time between reversal, and the inverse of that is the frequency of reversal, depend exponentially on some parameter of the flow, which means that even a moderate change in the parameter of the flow might induce very large change in the frequency of reversals. And changing even a little bit the parameter of the flow could put the system in a state where reversals are very improbable. And it seems to be observed also for the Earth's magnetic field that there are very long duration without reversal. So it could be explained by a change just on some parameter of the flow and does not require a drastic change in the flow characteristics. So now if I want to compare the different systems that have reversal with the normal form, I just write the normal form with some noise terms. So zeta is a noise of amplitude, and I define how the dipolar amplitude is related to theta, and I can simulate it and compare with what is observed in the model in VKS and for the Earth dipole. So they're qualitatively similar, and they have long duration in one polarity, and then suddenly they reverse towards the other polarity. Roughly the three of them. You can identify phase where they are. You can identify, at least for the two first, but for some of the problem related to there, some overshoot at the end of a reversal. They have excursion. So if you want to test a bit more in details the fact that it might be close to a saddle node bifurcation, then we can compare the shape of the reversal for the different system and the shape of the excursion. So that simulated that from VKS, so in gray it's the different realization, in dark it's the average over the different realization for the model for the VKS, and that's for the Earth dipole, so it's extracted from geophysics measurements. So what you can say on the three regime is that reversal first start with a slow phase and are followed by a fast phase. The fast phase ends with an overshoot. At least it's very clear for the model on VKS. It's claimed by geophysicists. Then you can compare also excursion and see that. Whereas excursion do not have overshoot, that's what I observed for reversals. So it seems to be at least qualitatively in good agreement. And so just to say a few words at that point on reversal. So it's a process that is activated by turbulent fluctuation. But it's important to realize that it does not require a large amplitude of turbulent fluctuation.
Right.
Sure.
So these sort of combine, those to combine others into two forms of unsteadiness. One is what we classically call turbulence, this is a very high frequency, low amplitude fluctuation. And then there's something you might characterize as a meandering of the mean fluid. Low amplitude, large amplitude, low frequency. Just like in the wake behind the chimney, the wake flaps slowly, but we don't call that turbulence. Within that, there's very high frequency, small amplitude stuff we do call turbulence. two kinds of unsteadiness. So how do you know? So you assert that it's the turbulence which is triggering the reversals. How do you test or know that it's the small amplitude, high frequency stuff, and not just the slow meandering of the flow from one, locking into one mean flow, then into another, then into another, and around fashion?
I mean, the bifurcation, as I describe it, is just the competition between two magnetic modes, and is not related to a drastic change of the velocity field.
How do you know that?
So, because
In the experiment.
in the experiment, we haven't, like, look at the phase parameter. We have very different regime where we have evolution from, all these regimes occur from stationary, then oscillatory, and then at the boundary, we will have some reversals. Do you expect to have like a flow bifurcation in all these regimes, in all these pockets? No, I don't think so. And we don't have measurement of that.
The high frequency stuff, the magnetic Reynolds number at the large scale is about 30.
So the magnetic Reynolds number.
Yeah, it's about 30. I guess that's based on your color size or something.
Yeah.
Turbulent fluctuations will be in a scale. So the magnetic Reynolds number on the scale for turbulent fluctuations will be tiny.
Yeah. So once again,
So it's completely diffusive. It's hard to see how you push drag the field into the
So
direction.
the thing is, okay, exactly. The thing is, when you close to the saddle node bifurcation, okay, you need fluctuation of very small amplitude. Actually, at the onset, they go to 0. Okay?
There's something else much bigger hitting it all the time.
How do you know it's coherent and it acts coherently to coupling the two modes? Actually, look at the time series. They're very regular. The oscillation, the nonlinear oscillation. How can something hit it very, very hard and the system maintains its periodic behavior? So reversal, our description, process activated by turbulent fluctuation, but what is important to realize that it does not require very large turbulent fluctuation. Actually, when you're very close to the saddle node bifurcation, the amplitude of the required turbulent fluctuation goes to 0. If there are turbulent fluctuation large scale, or if there are large turbulent fluctuation, or if the turbulent fluctuations are very efficient at coupling these two modes, then what you will see is that the domain in which you will have reversals activated by the fluctuation will be large. But in all cases, this domain will be at the boundary between a stationary and an oscillatory behavior that is driven by the coupling between two magnetic modes. And the physics of that is the magnetic field does not vanish, actually, it just changes shape. So it goes from dipolar, description, to quadrupolar, and then the opposite dipolar. For the S and for VKS, at least in the regime close to exact counter rotation for VKS, it's likely that a dipole and a quadrupole are involved. And it's in different model of the S, it has been observed that dipole and quadrupole are two modes with onset very similar. I want to say at that point something is that the bifurcation is very generic, and even if modes do not have different symmetry, then you may have the bifurcation without symmetry breaking, and it's generic in the sense that what we can prove. Suppose you have a system in which B equals 0 is unstable, and creates the first mode here. Suppose it is unstable in the second direction and create another pair of modes. Then suppose that the coupling term will get these modes close to a saddle node bifurcation. So you have two modes, a stable and an unstable one, that are very close. Then the system, if there is a saddle node bifurcation, has no other solution than to create a limit cycle that connects these 2 points. You can convince yourself just by saying, so suppose the two modes collides, what happened to the trajectory in this phase space? So what happened to initial condition close to here? They could go to another fixed point, but the only other fixed point when they have collided is this point here, and it's unstable. So it can only describe a cycle. So it describes a cycle. Suppose it's a cycle like that. Now, it's not possible because in a plane, limit cycle must contain a fixed point. So that is not admissible. So the only fixed point left is b equals 0. So the limit cycle must contain b equals 0. Suppose it contains b equals 0, but does not go through the opposite fixed point. So it goes like that. Then you realize that the invariance b gives minus b will create some problem because the opposite cycle will intersect with this one. So that's not admissible either. The only way that has the system to evolve at that point is to create these cycles that connect this point here. So that's the standard knot bifurcation that transforms a stationary solution into a limit cycle. And in the vicinity of this bifurcation, then turbulent fluctuation, even very small, might drive reversal.
You're slightly confusing. Can you draw a diagram where your parameter is going along in the horizontal plane?
You want me to do a 3D picture, a 3D plot on the plane?
Yeah. Possibly could.
And the symmetry. And then if I change the couplings, I get closer.
Can you use a white chalk?
Yeah, white chalk.
I'm not really sure I understand what you want. And then when they hit, they will describe the cycle like that, in this plane. No?
I'm wondering where this subtle nerve bifurcation is. Is it higher values of the magnetic Reynolds number?
Say again?
Where's the subtle nerve bifurcation? Oh, it's basically supercritical values of the magnetic Reynolds number.
In our case, it happens when you change the velocity, the difference between the two disks, the velocity difference between the two disks.
So the initial bifurcation is a linear instability. So basically, you've got two states coming in at once.
Yeah.
Yep.
So
and then you're claiming they collide in the cell node.
Yeah.
Okay, and then you're looking at the behavior around that.
Okay. If you reduce the dynamics in that plane, that's the equation for theta I've described before. Okay. So I could discuss a bit other system in which this is observed, but I don't know how much time do I still have. So
A bit non-generic though, colliding in a subtle node later on. A higher magnetic Reynolds number. I mean, that's the thing that's slightly confusing. Why is that generic?
So, I've shown you that if you have a pair of modes and that they collide, then it will evolve onto the limit cycle. So the only thing is, can you have or not limit saddle knot bifurcation with two modes? Then, if you have two parameters, then you can have one. Say you have two modes, and the second one go to the.
So it's all predicated on that subtle node.
Say again.
It all relies on the fact that you've got subtle node bifurcation at some supercritical value of the magnetic Reynolds.
Exactly. So, how much do you still?
How much have you got?
I will list a few examples in which this kind of behavior.
A few more minutes.
Sure. So, there are different systems in which you have the same kind of behavior. You might have the same kind of behavior. So, that system in which a large-scale field is generated on a turbulent background. So, suppose one of these systems is turbulent Rayleigh-Bénard convection. So, suppose you hit the bottom of a layer and cool down the top of the layer. Then you have the Rayleigh-Bénard instabilities and rolls are formed. And if you go very far above criticality, then system will evolve into only a large-scale roll. So there is a large-scale roll of convection. And this large-scale roll can reverse. It has been observed by different persons. So I think the first were Krishnamurti and Howard. But recently we had this paper by Liu and Zhang. And that's a picture extracted from their work. And maybe what we're working on now is that. So the system reverses. And if you look at time series, so it reverses between rotating in that sense to rotating in the other sense. If you look at time series, it remains for some value for long duration and then reverse. So it's really similar to reversal. And if our framework apply here, then it would mean that reversal occurs through the coupling with a more structured flow. That would be a dipole, the opposite of a dipole, and then a quadrupole. And that the system, instead of having all the large-scale velocity going to 0 and then increasing in the other direction, would prefer to create these other modes, so which means part of the counter-rotating walls appear at that boundary, invade the system, and finally reverse completely. So that's a possible mechanism for reversal in that system. Another system in which reversal have been observed is when you look at two-dimensional periodically forced flow. So that's from a paper of Someria. And so you force periodically a layer of fluid two-dimensional. So you have many arrays here, and in some regime of parameter, a large-scale field will be created, a large-scale flow will be created. This large-scale flow can have two directions, in one sense and the other one. And it has been observed here. So time series very similar to the reversals observed before. You can even see some excursion here. So maybe in this system again, and that's work on progress, so I cannot, we're still working on it.
That's the whole, so you've got a large scale flow, it suddenly stops and reverses.
So in our description, it will not stop actually. It will go into another state that invades the system from one of the boundary and then rotate in the other direction. It's like a dipole-quadrupole interaction. The system, instead of going to 0, it prefers to change its shape before reversing.
And you don't know whether the state is
Say again?
transient, and you don't know yet whether this transient state from one reversal to the other has been observed.
Yeah, we don't. No, we're working on that, but we suggest that this kind of evolution between two large-scale modes can be involved in the dynamic of this kind of systems. Okay, so I'm not gonna say a lot, but if you look only at the transition from stationary to traveling wave, from the transition from stationary state to a periodic behavior via a saddle knot bifurcation, this has been, and with not the notion of reversal, just a transition from stationary to nonlinear oscillation. It has been observed in different systems, again convection by Tuckerman and Barclay and Jennifer Seegers in numerical simulation of axisymmetric convection and by saddle knot bifurcation. Well, I have also a few other examples in which you have this saddle knot bifurcation that I could discuss more in detail if people are interested. So, vesicle in the shear flow displaces bifurcation, and even Josephson junction. Well, it has exactly the same structure, and that's constrained by the symmetry of the problem, actually. So, I'm almost finished now. I'm just gonna say a few more words on the magnetic field behavior. So, as I say, the system evolves. Our understanding of the dynamic is that there are two modes. These modes are coupled and then go from a regime of stationary to a regime of nonlinear oscillation, and the transition is what is called a saddle knot bifurcation. Turbulent fluctuation at the boundary of the saddle knot bifurcation will drive reversal. So it's interesting to notice that this bifurcation scenario drives the system also when you're above the onset of the saddle knot bifurcation. You're in a regime where the magnetic field oscillates in a noisy, maybe noisy oscillation, but it will get to periodic oscillation. So it's tempting to link this behavior with what is observed with the sun. So if we want to say that this is related to something observed in the sun, then we would like to say that the dynamic of the magnetic field of the sun comes from the interaction between two modes, that these two modes are coupled and achieve a saddle knot bifurcation. And then if you look at these two modes, you can say that one will have lots of energy, its energy decrease, and when it decreases, the energy of the other mode increase, and then the energy of the other mode decrease, and the energy of the first mode increase. And there is an exchange of energy between these two modes in a periodic fashion. So maybe it's really far more complicated with the sun. Maybe the magnetic Reynolds number is far larger. That's quite possible. And maybe many modes are involved. I just identified in this paper by Knack and Stenflo, it's from Knack and Stenflo the same. They had they identified these properties that they found interesting was that If you look only at axisymmetric modes, if you look at the dipolar component, it oscillates with a period of 22 years. The octuple L equals 3 is roughly in phase with the first, with the dipole component. But the L equal 5, I noticed that the L equal 5 component, spherical harmonic, of the magnetic field oscillate in a different way, and that when the dipole component goes to 0, then cis component get very large, and when the dipole component is large, cis component get very small, and in a periodic way. So this might be in agreement with a scenario in which cis oscillation comes from the interaction between two modes that achieve a sudden knot bifurcation, and that the energy is exchanged between one mode that is dominated by the L equal 1 component and another mode that has more energy in the L equal 5 component. And I will stop here.
One of the questions being before, but still have some more.
Yeah, I mean, I'm not quite sure what the significance of the quadrupolar is in your model. I mean, presumably you need it to get this sub-node bifurcation. But is there a simpler scenario where you have the dipole bifurcation, either up or down, and then at some finite value of the magnetic Reynolds number beyond the bifurcation, you get a heteroclinic connection between the two different symmetry states. And that gives birth to periodic orbits go close to both states. And of course, you've got noise, so that could essentially disrupt the periodicity a little bit to give you the sort of signals that you see.
And then how would you explain the periodic behavior of the
Periodic behavior?
Yeah.
Well, the periodic behavior will be the underlying periodic orbit, which is born when the heteroclinic connection breaks up. Right?
Yeah.
So that's a sort of a very minimalist system. You just need dipole bifurcation. Pitchfork.
But then, in which phase space do you represent this behavior? So you have the dipole, and then what's happened?
So there's a dipole pointing up there, there's
Yeah.
a dipole pointing down there.
And what
then
the other axis?
Yeah, and then at some point, as your magnetic Reynolds number increases, you generate a heteroclinic connection between them.
And what's happening in the other direction? In which phase space do you represent that? Isn't it another mode in the other direction?
Well, I don't have to have them, no. Just have these two solutions here. The laminar state here, as it were, no magnetic field, and then a heteroclinic connection. And this is all the other dimensions reduced down to 1.
So you...
Well, maybe I'll sketch it for you in a minute. I mean,
Yeah.
you know, 3D.
Now, the thing is, also, if you would make this model and in 2 dimensions, you have to remember that heteroclinic connections are not, how do you say? They are not stable.
Yeah.
Stable.
No. Yeah, I realise that.
So I think that the scenario via sudden knot bifurcation is quite more robust.
Can I just ask about this second mode that you have? Maybe it's following on from Richard's question. What properties, what distinguishes that as the second mode? I mean, for example, on that one you've got m equals 0, L equals 1, m equals 0, L equals 5. And in your convection one, it looked like you had 2, and the other mode had 4. What's the property of the 4 cell one that makes it the other player in the game?
So you want me to describe how do the mode look like and which forcing term will couple them?
I thought you chose, you privileged the quadrupole and dipole just because the experiment showed them both. Isn't that correct?
Yeah.
Don't they come in?
And it's known in different model of geodynamo and parametrized model with alpha omega. It seems to be quite robust that the dipole and the quadrupole have a very similar onset.
Yeah.
So
Yeah, okay, so I can see it in that case that these two different things come in together.
yeah,
And so if you're close to that onset, then they should all be in play. Okay.
right, exactly.
Then if you say, look at the one that you had with the convection, you just showed one slide of turbulent convection, and it had, I think, 2 cells, whatever, and then you said they could both reverse via interaction with the 4 mode.
So for the convection, it was just mimicked.
Yeah.
So you can have C state.
Or one, yeah.
You can have C state,
And that's the other guy.
and that may be the other mode that could be involved.
Right. So how does that one come in this system? What's the justification, as it were, for this one? Like in the magnetic one, you say, "Oh,
So
they're
in
coming
the,
together."
in the magnetic one, I would say, okay, it's in different model, at least it's known that the dipole and the quadrupole are very close. Then in this one, no, we don't have proof yet, but it's quite natural that if you have cis mode, then a mode a bit more structured should be not very far from onset also. So until we have measured it, we can.
Rigorously to bring it in. The two things that are competing, they need to come in close by each other. That's.
Oh yeah. For
So
the
you're kind of postulating that
yeah,
that one.
yeah, exactly.
Any other questions? Exhausted us all. Thanks.